Hi everyone, welcome back. This is Dr. Rhonda Copel, and this is part 3 of our study of chapter 3 in the Burge text that we're using here, and this is going to be looking at the mole. And you may have heard about this if you've been in chemistry before. We're going to look at the mole and how that helps us go between numbers of particles and mass. So people use a lot of things to count, and they use depending on like what country you're in or whatever, but like a pair of something means 2, a dozen means 12, and so there are other things that we use in normal conversation. The mole, however, in chemistry is very specific, and it is telling us that if you have a mole of something, then you are going to have exactly 6.02 times 10 to the 23rd. Okay, so 6.022 times 10 to the 23rd. Get my pen back on track here. So 6.02 times 10 times 10 to the 23rd is a mole of something, and it doesn't matter what it is. It can be a mole of donkeys, it can be a mole of molecules, it can be a mole of whatever. And so it's the same as saying that you've got a dozen of something, you've got a mole of something. And so what it does though is it bridges that gap between the atomic level and the real world where we are. A mole is defined as the number of atoms in exactly 12 grams of carbon-12. So the number of atoms in 12 grams of carbon-12 is Avogadro's number, and that's 6.0221418 times 10 to the 23rd objects. We're going to typically just leave that at 6.022 times 10 to the 23rd. So a mole of anything is 6.022 times 10 to the 23rd. A mole of atoms can bring us from the AMU world to the world of grams. And so that's why we use it in chemistry. And it is like all conversion factors. You can use it right side up or upside down, depending on what you need to do to cancel out your units. So how we use this is by taking the atomic masses of atoms, elements, molecules, which we've learned how to do, and taking that and then allowing us to use that in reactions, because we're going to see that in our world things are going to react in mole ratios. And so that's why it's important for us to get a handle on the mole and to know how to use that in our calculations. So this first sample problem that I'm going to do here says a typical human body contains roughly 30 moles of calcium. Determine, first of all, the number of calcium atoms in 30 moles of calcium, and then the number of moles if you have 1 times 10 to the 20 calcium atoms. All right, so for the first one, part A, we start with 30 moles of calcium. So 30 moles, sorry, I keep doing my pen. I'm not sure why it's doing that. I'll tell it again, pen. Okay, so we got 30 moles of calcium. All right, and it wants us to know how many atoms are in 30 moles. So we know that our conversion is going to be Avogadro's number, so that we know that there are 6.022 times 10 to the 23rd atoms of calcium in 1 mole of calcium, because there are 6.022 times 10 to the 23rd anything. And this is a good time for you to check your calculator and make sure that you are putting it in there correctly. And what I suggest is if you have a calculator that has an EE key, that you enter Avagadro as 6.00 EE 23. And that's like calculator language for, 6.022, my bad. 6.022 EE 23 is telling the calculator in its own language that it's times 10 to the 23rd, okay? And that saves you all kinds of grief about using the proper parentheses and things like that. So if you put that in properly, you're going to get 1.807 times 10 to the 25th atoms of calcium. All right, and then going the other way, if you start out with 1 times 10 to the 20 calcium atoms, this time you're going to use Avagadro the other way. You know you got to have the atoms part down here, because just like in that first problem where we were canceling out moles to get atoms in our answer, we need to cancel out atoms to get moles. So this time the 6.022 times 10 to the 23rd is going to go down below, and then the 1 mole will go at the top. And if you put that in your calculator correctly, it's going to be 1.661 times 10 to the minus 4 moles of calcium. All right? So those aren't too hard, are they? Okay? So that's going from moles to particles. Okay? Moles to atoms. So not much hard about that. And then I've given you a practice problem to do. You will have to look up potassium, if you recall, is the symbol K, and you can look on your periodic table and find out what the atomic mass of potassium is, so that you can do your problem. Okay, so we know that we've done the molecular mass, formula mass with AMUs, okay? So now we know that the molar mass, or 1 mole of the substance, okay, we can now get the molar mass of 1 mole of substance. And we can do that in grams. And it's super simple, because it goes you calculate it just like you did the AMUs, but we're just going to use grams, because the Avogadro's number of atoms in 1 mole takes us to grams from that atomic world. Okay, so we know that atomic mass of calcium, for example, if the atomic mass is 40.08 AMUs, then its molar mass, a mole of calcium atoms, is 40.08 grams. Sodium, 22.99 AMU, molar mass is 22.99 grams. So it's the exact same magnitude of number, it's just a different unit when you're going from the atomic world, small, 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 to the real world where we can use it and do calculations with it. So if 1 AMU is 1.661 times 10 to the minus 24 grams, that's where 1 gram is equal to 6.022 times 10 to the 23rd AMU. So 1 mole of atomic mass is 1 gram. All right, so super easy, numerically equal molecular formula mass in AMU, exactly the same as we're going to see the molar mass of elements and of compounds. Okay, sounds pretty easy so far, right? Okay, so I've got this little picture here which kind of shows you going back and forth. All right, so if you've got grams to start out with, and you're going to moles, then you're going to divide the molar mass, or divide by the molar mass. If you're going back from moles to grams, then you're going to multiply moles times grams over moles. Okay? Same thing with particles. Avogadro's number is what takes us back and forth between particles and moles, or atoms and moles, or molecules and moles. Okay? So you can remember how to do that conversion, without having to memorize every little thing. Now, I have another thing that kind of helps me remember. And this came from me watching my dad hunt moles out in the yard. Long story, I'm not going to bore you with it, but if you go, you can't go under the molehill. So what that means is that if you're going to go from one thing to something else, you've got to go to moles first. So if you go from grams to moles, you're going to use the formula or molecular weight. If you go from moles back to atoms, you use Avogadro's number to do that. Okay? And so whether you're going this way, if you're going one way or the other, up the hill or down the hill, you use those same numbers. And so a lot of times when I'm working a problem, I'll do this. And so I'm going grams to moles. So that's going to be formula weight. See what I mean? So it's just a little thing to kind of help you remember. Okay, so the number of moles of carbon in 10 grams of carbon. So how many moles of carbon is in 10 grams of carbon? And then the second part is if I have 0.905 moles of sodium chloride, then what is the mass? And so that's going to equal so many grams of sodium chloride. All right? So whenever I'm doing these mole problems, what I need to do is figure out either the molar mass or the formula mass or whatever. Okay? So in this particular one, if I've got 10 grams of carbon, I start with that. Okay, now it wants moles, and so over here I'm going to have moles. So what do I know? What is the relationship between grams and moles? Well, I know that the atomic mass or molar mass is going to be the number of grams in 1 mole. So in carbon, there are 12 grams in 1 mole of carbon. Okay, and your periodic table may say 12.01 grams. Okay, either one. All right, and so I know that I'm doing this right because I'm going to get rid of my grams and I'm going to be left with moles. And so when I do that math, I'm going to have 0.8326, and I can use 4 significant figures, okay, moles of carbon. Very simple calculation, okay? Now with this one, I've got to figure out what that formula weight is of sodium chloride. So I've got to do Na plus Cl. Cl is 35.5 basically, and 23 point, can't remember, 23 point, or 23. It's 22.99. And double checking chlorine, 35.45. Okay, and I just looked at my periodic table. That's what I was doing. Okay, and so when I add those together, the formula weight for sodium chloride is going to be 23 plus 35.45, or 55.45 grams per mole. Okay, that's the molar mass of sodium chloride. So once I know that, I look at this. Moles is here, so moles has got to be on the bottom, so I can cancel that out. So that tells me 1 mole of sodium chloride goes on the bottom, And so the grams, which I'm trying to get to, with sodium chloride, goes on the top. And so when I do that math, I'm going to get 52.9 grams of sodium chloride. All right, so I've done Avagadro and done how many atoms, and I've done mass and done grams. So those calculations, you just got to remember that this formula weight or element weight is, you've got to use that for each component in your calculation. So here are your practice ones, and so go ahead and do those. You should have an answer sheet with the correct answers for all of these so you can see if you're doing them correctly or not. And there's another one, okay, for your practice, okay? So you should be able to do it. You're just building all these skills that we have been working on up to this point. So empirical formula is, we've mentioned this a little bit before, and so an empirical formula I'm going to cover in another video. All right, have a great day.